observability versus monitoring. So first of all, just recap what is monitoring observability. So monitoring is about tracking predefined metrics and alerts. The emphasis on the word predefined, it tells you when something is wrong based on known conditions, whereas observability is about having enough data in the context of logs, metrics, traces, events, and also the right tools to understand why something is wrong, even in complex, unpredictable systems. So in short, monitoring answers the question, is it working? While observability answers, why isn't it working? Making observability the deeper capability that enables DevSecOps teams to detect, diagnose, and resolve issues proactively. Although it's misleading, I would say, to frame monitoring versus observability, because they're not really substitutes for each other. They actually complement each other. Monitoring is still essential. It gives you alerts when known thresholds or rules are violated, such as, let's say, CPUs greater than 90% or services down or whatever the thresholds are in every case. Whereas observability builds on that by giving you the context and depth to understand unknown or unexpected issues, such as tracing a spike in CPU back to a faulty release or a misconfigured security scan. You can think of it this way: monitoring tells you that something broke, observability helps you understand why, and together they form the foundation of reliable, secure, and resilient DevSecOps practice. Okay, this chart talks about observability, observer, and observability, different context of observability. When we talk about observability, it starts with the basics: observable data, logs, metrics, and traces, as well as the observers, people or tools that make sense of the data. Observability itself is the ability to bring these together so teams can understand the health and behavior of their applications. It goes beyond just having monitoring. It's about seeing why something is happening, not just what happened. This distinction is critical in DevSecOps because it allows teams to detect and diagnose issues quickly across development, security, and operations. Taking it a step further, continuous monitoring focuses on detecting compliance or risk issues, especially in financial or operating contexts, while continuous observability extends this into the DevSecOps pipeline. Here, the focus is on telemetry from applications, infrastructure, and runtime environments, enabling teams to uncover not only performance bottlenecks, but also security, compliance, and privacy risks as they happen. In practice, this means shifting from reactive incident response to proactive risk management, giving organizations both agility and confidence in delivering secure and reliable software. Yeah, this chart can bring up the point that testing isn't sufficient when you're talking about observability. Testing can tell you if a feature passed or failed under certain conditions, whatever the test conditions are, but it doesn't always explain why something failed or what's happening inside a system. So observability is needed for correct test verdicts. Without telemetry, logs, metrics, and traces, you can misinterpret test results. For example, a test might fail due to an environment issue, not a code defect. So observability makes that difference visible. Observability supports debugging as well. So when tests fail or incidents occur, observability data is what allows engineers to trace behavior across the systems, reproduce conditions, and identify root causes quickly. It can also determine system features that are needed for observability. So systems should be designed to emit the right data, structured logs, meaningful metrics, distributed traces, so that observability tools can provide those actionable insights. You want to build observable systems, don't treat observability as an add-on. Design it in as a primary feature for system behavior, not as an afterthought. Provide multiple windows into functions, so give teams different ways to look inside dashboards, alerts, traces, metrics, so the issues can be understood from multiple perspectives. In general, testing shows you what happened, but observability shows you why it happened. And building observability into systems ensures that both accurate test results and safer faster debugging in a DevSecOps pipeline. Here's how cloud-native applications tie directly into the continuous observability process in a DevSecOps context. Dynamic and ephemeral by design, cloud-native applications run on containers, microservices, and serverless functions that scale up or down rapidly. Continuous observability is essential because traditional static monitoring can't keep up with these constantly changing environments. You need to have telemetry at the core, so cloud-native platforms like Kubernetes, Service Mesh, and managed cloud services are built to emit logs, metrics, and traces natively. This makes them ideal for plugging into continuous observability pipelines, where telemetry is collected, correlated, and analyzed in real time. Security and compliance integration with cloud-native infrastructure and applications are often defined as code. Continuous observability can track not only performance, but also runtime security, compliance drift, and policy adherence across clusters and services. Automation and feedback loops exist. So continuous observability and cloud-native systems feed automatic alerts and remediation workflows. For example, if an API call pattern looks suspicious, or if a container violates a compliance policy, observability data can trigger automated security responses in the CI/CD pipeline. End-to-end observability is referring to this because cloud-native applications often span multiple services and environments. Continuous observability provides a unified view across development, security, and operations, ensuring teams see the same truth. Bottom line, cloud-native applications generate the telemetry that continuous observability depends on, and in turn, continuous observability ensures these fast-moving distributed systems remain secure, compliant, and resistant in real time. This is an example, kind of a case story. So the Swift hack, which is something that happened in 2016, February 2016, and North Korean attackers exploited weaknesses in the Society for Worldwide Interbank Financial Telecommunications, SWIFT network, specifically targeting the Central Bank of Bangladesh. They attempted to steal $1 billion through $1 billion through 13 fraudulent transactions routed via the Federal Reserve Bank of New York. Although analysts in New York managed to stop most of the transfers, over 81 million were successfully stolen. Here's how the lack of continuous observability enabled the attack. First of all, printer and logging features. The Bangladesh Bank Swift terminal printer, which was supposed to print confirmations of transactions, was disabled by malware, and the logs were manipulated to hide the evidence. There was no real-time cross-check, so without continuous observability, fraudulent transactions weren't immediately flagged or correlated against normal banking systems. There was delayed detection. By the time anomalies were noticed manually, much of the damage had already been done. So how did improving observability, how could it improve the outcomes? First of all, by having real-time telemetry. If transaction data, logs, and system health metrics had been continuously observable, the missing printouts and altered logs would have raised immediate red flags. If you had behavioral anomaly detection, observability pipelines could have detected unusual transaction amounts, timing, and destinations against established baselines. Also, cross-system correlation with infrastructure as code observables and multiple monitoring metrics. Suspicious gaps like a failed printer, alerted logs, and abnormal transactions could have been tied together to trigger automated alerts. Bottom line, the Swift hack illustrates that security controls without continuous observability do leave blind spots, and by designing systems that continuously emit, correlate observables, organizations can detect fraud and cyber attacks earlier, reducing damage and strengthening resilience. This is an actual case story. Actually, it's surrounding the book written by Ben Hookup. It's called The Hacker and the State. It's an interesting read. He says every case of hacking involves someone observing the wrong thing or the right thing at the wrong time. So collecting time-related data is important too. Who can contain source data for the earlier Swift story. So if you want to know more about the Swift case that we just talked about, it's discussed more in that book. Continuing on the next slide, with a little more information from the book. It says DevOps observability requires knowing how operations work and who might break them. Again, there's examples of previous failures that allow growth and expansion.